Good morning. I'm Yagisan from Group 5. My group's project is two beam interference, collimated beams. A collimated beam of light is defined when every ray within the beam is parallel to every other ray. The superposition of two waves is known as two beam interference. The Michelson interferometer produces interference fringes by splitting the light beam into two parts and then recombining them after they have traveled separate optical pathways. So first I'll talk about the Michelson interferometer setup. The light releases the light source releases a light beam that hits the beam splitter and separates the light beam into two. Both beams will have reduced amplitude and will travel in a perpendicular manner. The reflected light beam from the two mirrors will travel back to the beam splitter and will be transmitted onto the screen. Next is about the various fringe patterns due to the alignment of the interferometers mirrors. There are various types of fringes formed by the Michelson's interferometer, which is circular, concentric fringes, curved fringes, and also straight line fringes. In order to get concentric circular fringes, the both mirrors should be aligned perpendicular to each other. The beam splitter also needs to bisect the angle uh, between the two mirrors at a 45 degrees. Next, the distance of the movable mirror from beam splitter is turned to a slightly greater or smaller magnitude than of the fixed mirror. Then the beam expander is placed and its height is adjusted to get circular fringes. To get curved fringes, you just need to tilt the movable mirror at a small angle. Now that they are aligned at a non-perpendicular manner at an unequal distance, curved fringes will be formed. To get straight line fringes, the alignment of the mirrors is modified so that the fixed mirror and the tilted movable mirror are placed at equal distance from the beam splitter. Next, we'll see about the effect of mirror translation on fringe pattern using a piezoelectric driver. The Michelson interferometer is actually very sensitive that even the smallest discrepancy can cause misalignment. When electric current is applied to a piezoelectric crystal, it modulates the arm length between the mirrors and causes misalignment in the interferometer setup. This interference will then cause changes in the fringe pattern that is shown on the screen. Fringes, fringes are formed due to interference. When both light beams are superimposed, then they interfere with each other. The contrast between the dark and bright fringes is what tells us that there is interference. Without interference, there will be no contrast. There will only be a spot on the screen. Achieving a high fringe contrast is desirable to get the best interferometer sensitivity. Since real-world application is not as ideal as the above mentioned theory, a suitable alignment is very important in this case. And in conclusion, Michelson's interferometer is a very useful optical instrument. With the interference principle, we can use it as an instrument for the wavelength measuring of an unknown light source, refractive index measuring for an optic, velocity measuring of light along two different locations.